So in the previous videos, we have seen the factors upon which the capacitance of a given capacitor depends. And in this video, let us look at another thing. So in that video, I had told you that we are assuming that there is vacuum between the two plates, or in other words, there is nothing between the two plates, and that is the reason we were taking the permittivity of vacuum to do the calculations. Now let us wonder what happens when we actually do not have space, or we do not have vacuum between the two plates, but we have some other material. So first of all, if I have some conductor, let's say some metal, what would happen? Obviously, if I attach a battery, the metal will, so if I have some metal between the two plates, right, filled it up, obviously the connection will be, so the circuit will be complete, and obviously the current will start flowing in the circuit. So obviously nobody is that stupid, and so we will not insert a metal. And obviously, because we've learned in the under the topic of the electrostatics of conductors that the electric field inside a conductor is zero. Why is that so? Well, because I have some positive charge on this plate and some negative charge on this plate, and that means I have an electric field going from this plate to that plate, right, in that direction. Now if I have some metal, let's say I'm not touching it to both the plates, so that metal, so the electrons of this metal are free to flow, so all those electrons will be repelled by this negative plate and they'll get accumulated on this end, and they'll leave a net positive charge on this end, and this metal will obviously create an electric field in the opposite direction, see, in this direction, and the electric field of the capacitor was already in this direction, and this electric field of the conductor will cancel out the electric field of the capacitor. But yeah, obviously we will not do that, because there are chances of a short circuit happening, and that will defeat the purpose of a capacitor. We don't want the current to be flowing, and so we will not insert a conductor between the two plates. What we will be doing is we can insert an insulator between the two plates. So that insulator has actually two basic functions. The first function, which is very obvious, is to keep these two plates from not touching each other, right? So they'll act as a spacer between the two plates, and that will ensure that the two plates do not come into contact and the circuit is not complete. So that's the first function. But the second function, which is even more interesting, is that it actually changes the capacitance of the capacitor. Now let us look at that in a bit more detail. So basically we have two types of insulators that you might have studied this earlier: polar and non-polar. So what is polar? Well, water is an example of a polar substance, which means that if I have a water molecule, so this is an oxygen atom and I have two hydrogen atoms, because oxygen is more electronegative, it will pull the electrons from hydrogen towards it, and causing a net partial negative charge on the oxygen atom and a partial positive charge on the hydrogen atoms, right? So there's already some charge separation on the water molecule, and that is why it is polar. On the other hand, molecules like maybe methane or carbon dioxide, such molecules are non-polar because they do not have such polarities. So let us take both examples one by one. Let's say if I have some polar, so I'll not draw a complete structure again like this. What I'll draw is, let's say I have some polar substance inserted between the two plates. So obviously the dipoles will not be aligned, and they'll be present in random directions, right? So let's say I have one molecule here which has its positive end on this side and negative end on that side. I have another molecule whose positive end is on this side and negative on this side, maybe another molecule whose positive is on this side, negative on this side, and they'll be just arranged randomly, right? And I have many such molecules. Obviously I'll just draw a few of them. Positive on this side, negative this side, positive here, negative here. So they are all random, but because I have some external electric field due of the capacitor here, so if I begin charging this capacitor, I'll get an electric field in this direction. Now this electric field will make these dipoles aligned. Remember, we have a torque on the dipoles in a uniform electric field, so that torque will align all these dipoles, and what we'll end up getting is somewhat like this. So I'll quickly just fast forward this section and show you what happens if I have an electric field on such an arrangement. So here we have the polar molecules being arranged in line with the electric field, and now so this is what happens if we have a polar substance between the two plates. But if we have a non-polar substance between the two plates, what will happen is when we have an applied electric field, the electron cloud of that particular molecule will shift. So because the atoms cannot move from their places, right, they are bound there, and also the electrons are bound because this is an insulator. But yeah, the electron cloud can actually shift to one side, and there will be some induced polarity in that particular molecule. So the end result in both the cases will be similar. Obviously the extent will depend on the particular substance that you are taking, but the end result is that all the molecules will be aligned in such a way that the more negative side is obviously on this side, and the more positive side is on this side, which is in line with the electric field. So this is kind of the end result of whatever substance you're taking. And so right, and now if you observe, we have, so here in the central part of this substance, we have some positive charge, a positive, negative, positive, negative. And so if I take this section here carefully and I count the amount of negative charges and positive charges, so I have a positive, I have a negative, I have a positive, I have a negative, negative, positive, negative, positive, positive, negative, positive, negative, negative. So I have almost equal amounts of positive, negative charges. So in this whole area, the amount of positive and negative charges is almost equal. So this whole section is neutral, right? Overall, I have charge separation in smaller parts locally, but overall this whole section is neutral. On the other hand, this here, the last this here part, this last section here, I have been left with some negative charges on this side, and I have been left with some positive charges on this side, and this is not neutral. So this negative charge on this side will actually cancel the positive charges on this side. What I mean by that? Well, I have some charge separation left. So if I repeat, in the central part of this substance, the overall charges will cancel out because the amount of positive and negative charge will be equal. But I will be left with this small layer of negative charge on this side and this small layer of positive charge on this side. This positive and this negative the small layers of positive and negative charges will create an electric field. So that electric field will go from this positive charge to this negative charge, this negative side, and that will be acting in this direction. See, and that will be opposite to the electric field of the capacitor. And so this electric field, the electric field which is induced due to the substance inside the capacitor, will be opposite to the electric field of the capacitor itself, and so the net electric field will be reduced. Now if the net electric field is reduced due to this substance that I have added, so firstly this substance that I have added is called a dielectric. I'll just name it. It's called a dielectric. So when I add a dielectric, ECTRAC. So if I add a dielectric between the two plates of the capacitor, this actually reduces the electric field between the capacitor. And now now let's see what effect this has. So remember, C equals Q upon V, and remember the voltage is nothing but electric field times resistance, right? So the voltage or the potential difference between the two plates depends on the electric field. So remember V equals ED. We saw that in the last video. So if the electric field between the two plates reduces, if this electric field goes down, the potential difference V also goes down. And if V decreases here, C will obviously increase, right? Because V is in the denominator. So V reduces, C increases. So the net effect we have is that in such a case, by inserting a dielectric, we are able to increase the capacitance of a given capacitor. So yeah, that is the effect of that is the basic intuitive idea behind the effect of a dielectric. What happens if we insert a dielectric or such a dielectric, which is just a substance, between the two plates of a capacitor. So that is the intuitive idea behind it. And the next video we'll be looking at the mathematical aspect of this effect.